Okay, let's get started. So just a couple reminders. First off, Lab 5 has been posted. It was posted last Tuesday, so please get started on that sooner rather than later. I know Thanksgiving break is coming up. I'm not an idiot. I don't expect you to sit around all Thanksgiving and working on the lab. I think it would be to your advantage to try and get some of it knocked out before you go on break, because I think if you come back after Thanksgiving break and you haven't started on it yet, you're going to have a bad time. So please, 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 even if you just get the design phase out of the way, right, that's going to save you a lot of time when you get back from break. I am going to give you time on Tuesday of next week. Tuesday is basically a work session. Come here, work on the lab, ask questions. I'll help you out. I'll give you pushes in the right direction if you get stuck. I think I'll have at least one other TA here as well. So please come treat Tuesday's classes like one big giant office hours. I'll also have additional office hours on Monday and Tuesday next week that I'm going to post to the calendar very soon. So keep a lookout for that. What else? I think that's about it for now. We got we're almost done, right? After this we have 3 more classes, right? 1, 2, 3. We've got a work session, we've got 1 more class with material, and then we've got exam review, and then that's it. Final exam, we're done. So we're getting real close. Any questions for me about homework, labs, schedules, et cetera? We good? All right, cool. So today, not going to look at any high-level state machines today. I don't know if you consider that a good thing or a bad thing. We're going to look at some different stuff today. So last section, before the last exam, we talked about adders. We talked about carry ripple adders. We talked about how slow they are, right? So today we're going to talk about an updated form of an adder called carry Lookahead adder. And then we're going to talk about multiplication as well as some other stuff that I want to talk to you about as well. So let's get started with talking about some of these new components. This over here is a full adder. That's what we use with the carry ripple adder, right? That's what we use over there. This is the components that we use for the carry Lookahead adder. So it's slightly different. We see the outputs listed here are G and P. You can tell me what the G and P are for? What does that mean? The G is for, yeah, generate a carry bit. So G is going to be true if I generate a carry bit. What's the expression? Do you remember what the expression is for G? G equals AB. It's easy, right? If A is true and B is true, then I need a carryout bit. It's as simple as that. I'm creating a carryout bit, right? Creating a carryout bit. Okay. What is P for then? P stands for what? Yeah. Propagates. So that means if I have a carry bit coming in, I'm going to pass it along to the next guy, right? I'm going to pass that carry bit on to the next guy. So what was the equation for P? How does P equals, yeah, A plus B. And then we have to AND that with Cn in order to determine, right? But that actually, so this result here, right, is just going to be, well, yeah, it's just going to be this part, A plus B. We'll worry about the Cn piece later. We're going to get to that part later. So this component here, we're no longer generating the carry bit out. Right? We're just generating these 2 out. So my question for you, my first question for you, right? How does it compare in terms of the number of gates? More gates, fewer gates, same number of gates, right? And then how does that relate in terms of delay? So they both compute S. But that's not going to change. That's going to be the same. That part is going to be the same. So the question is, do we use more gates, less gates, or the same number of gates for G and P as we do for carry out? How many gates do we use for carry out? Does anybody remember our full adder? How do we generate carry out? I'm sure you've got it available somewhere. Did you try to figure it out? How many gates do we use? Well, it's 3 AND gates and an OR gate. That's exactly right. We use 3 AND gates and an OR gate to generate this carry out bit. Okay? So then how many gates do we need to compute G and P? Well, that's easy, right? 1, 2. That's it. An AND gate and an OR gate. So in that sense, we're saving gates for this particular component. We're actually saving ourselves some gates. That seems like a nice thing. However, it's not going to last. So for a carry lookahead adder, if you remember from the video and the Xi book, it actually uses more gates than a carry ripple adder does. It uses quite a bit more gates than a carry ripple adder does. So that kind of leads us to the next question. Here is our carry lookahead adder, and here's that component that we were just talking about, right? In the Xi book and in the video, we've got this giant block down here that says carry lookahead logic. But nobody's ever shown you what that actually looks like, right? What the heck is in there? What does that circuit actually look like? Well, I included these expressions down here to kind of help us sketch together this circuit. I kind of like to do that together right now as a group so that we can see how this thing actually works. Let's start over here on the right side and work our way to the left. So on the right side, I've got G and P coming in, right? I've also got my carry in bit coming in. So if I want to know, right, whether or not a carry out bit is coming, what do I need to do? Well, I just need to apply those expressions. A carry out bit is going to happen if, under what conditions? Under what conditions do I have a carry out bit? What's the expression look like? CO on this diagram, right? C0 equals what? What's the expression? G or P and C in. Right? G means I'm going to generate a carry-in bit, or propagate means if I have a carry-in bit, then I'm going to continue to propagate it. Right? So in that case, if I want to sketch this out as a circuit, what does that look like? I need an OR gate. G is going in there, and then I need an AND gate with P and C in. Everybody with me so far? Everybody with me so far? Okay, so let's take a look at the next thing. So this is C0 coming out, right? This is C0 coming out. So now we've computed this one, and C0 goes off and it does its thing with the next adder. Okay, we're not going to worry about that part. I'm focused on this carry lookahead logic block. So now I want to compute C1. Right? I want to compute what C1 is. And so how do I get C1? C1 is going to be the same process, right? It's going to be based on G1 or P1 ANDed with C0, right? So I can use the same expression. C1 is going to be equal to G1 or P1 and C0. Right? So where does the simplification come in? So far, it looks like I'm actually just doing the same thing as a carry ripple, where I have to wait for this to be computed in order to generate the next value, right? It seems like I'm not gaining any extra time. What's the big deal with this carry ripple adder? Well, consider that C0 we computed as a function already, right? We said C0 is equal to G0 plus P0 Cn, right? And so we're going to get this value a lot sooner than we're going to get this value, right? We're going to know what Cn is a lot sooner than we're going to know what C0 is, right? We're going to be able to compute that faster. So why don't we just take this and substitute it in for C0? Why don't we just substitute it in? So what we now have is C1 is G1 plus P1 and G0 or P0. Right? So the equation becomes a little bit longer. You can actually see it down here as well, right? You can see it down here. And then what I'm going to do is distribute the P1. So what we're left with is G1 or P1 and G0 or P0 and C in. And what you notice about this equation is what? It doesn't depend on C0 anymore. I don't have to compute this carry out bit anymore necessarily in order to determine whether I'm going to have a carry out bit from the second place. Yes? I want P1 on this last one. Did I do this wrong? Oh, I'm missing a term. Thank you. P1, P0, right? Perfect. Think about what this is saying. This means I'm going to have a carry bit in this position if I generate a carry bit in this position. That's what G1 is, right? If I propagate a carry bit and the person next to me generates a bit, so this position generates a carry bit and I propagate it, or if I propagate it and the person next to me propagates it and I have a carry in bit coming from the very beginning, right? Those are the three possible cases that I'm going to have a carry in bit. The nice thing is, for me, I can compute G1 and P1 very quickly. Very quickly. It's a single gate. It's a single gate in each case. So I can compute these values very fast. Very, very fast. They don't depend on the carry in bit at all. They just count for A and B. Consider the case where P1 is 0, for example. Just immediately then, those two are gone. They don't matter anymore, right? These two terms just disappear if P1 is 0. Automatic, right? So here's the expression for C1. If I want to sketch this out with a circuit, I certainly could. I'm kind of regretting my use of whiteboard space here at the moment. I should have done this a little bit better. So I need, I'm going to use a 3-input AND gate just to make things a little bit easier for us. So I need a 2-input AND gate, a 3-input AND gate, and that guy, and an OR gate. So here's my OR gate, G1. Here's my 2-input AND gate, and my 3-input AND gate. I'll have to make some room. Let me get rid of some of this stuff so I have room. The bottom equation is the only one that we really need anyway. And so this is P0, this is G0. So those signals need to come over, like so, right? P1 is going to go here and here. P0 then is also going to come around and go in this very last one, as is C in. Oh, this is a horrible drawing, I'm sorry. Oh gosh, what is wrong with me? I drew this horribly. I hope you get the point, however, despite my ugly drawing. So you can kind of see what's going to happen if we keep going along this process, right? How many gates am I going to see for the next bit over? How many gates am I going to see for this guy? It's going to be more than this. Or what's the equation? It might be better than trying to draw out a crappy circuit like I'm doing. What's the equation for C2? I know it's on the slide, but work through it step by step. We know that C2 is going to be G2 or P2 and C1. Well, we know what C1 is. C1 is that equation that I'm now regretting that I erased off the whiteboard, because we're going to substitute it in, right? We're going to substitute in C1. So we could say C2 is equal to G2 or P2 and G1 or P1, C0 or P1, 0, C. And then we propagate this guy. For C2, we then get a much longer expression, P2, G1, or P2, P1, C0, or P2, P1, P0, C in. So it's a longer expression, and the last one's going to be even longer than that, right? But what are we saying here? I think, if the expression is making you anxious, just break it down. What are we saying? I'm going to have a carry bit here if I generate a carry bit, or if I propagate a carry bit generated by the guy next to me, or if I propagated a carry bit that's propagated by the guy that's next to me, that's been generated by, actually this should be G0, right? Or, you know, if I propagate a carry bit that's been propagated by the guy next to me, that's been propagated by the guy next to him, right? So what does that mean? That means what we're actually saying, how do we get the speed out of this? P0 now becomes a very important signal for speed. If I know that P0 is not going to propagate, I immediately rule out a whole bunch of terms, right? Just boom, right off the bat, gone. Just rule out a whole bunch of options. If I know that P1 doesn't propagate, then anything that has P1 in it is instantly gone, right? Instantly gone. So I'm actually computing things way ahead of time, whether or not I'm going to propagate or generate a carry bit. So I'm going to know whether that carry bit's coming long before the actual sum is even computed. Does that make sense? Does that make sense to you guys? So how many gates do I have here? I'm not going to draw them out because it's just going to get even messier, right? I've got 1, 2, 3 AND gates and a 1, 2, 3, 4 input OR gates. So you can kind of see the pattern, right? I had 1 AND gate, now I had 2 AND gates, now I had 3 AND gates. For the next one I'm going to have 4 AND gates. My OR gate's going to have an extra input as well each time around. So I'm just basically adding on another propagate term to each equation. Does that make sense? Other questions about this? This is really the whole magic. The whole magic of the pattern.
How many gates you're adding in there? Like if you just, instead of multiplying or not, just basically write out the circuits like the unmultiplied out equations.
The undistributed version?
Undistributed version.
Yeah.
Only have 2 gates per equation.
2 gates per equation. Say that one more time.
You have 1, 4, and 1 AND per equation, and you're feeding the output of that equation to the next one, so only 1 OR and 1 AND.
So you're saying if I use this, right?
Yeah.
Basically, I use this.
Right. And you just like plug C1, the wire to the C1 into that instead of like pulling the original inputs.
I see what you're saying, but the magic here really is using the expanded version because that's what allows me to determine my propagations way ahead of time. I realize that I'm still computing C1 this way, right? I realize that, but the speed really comes from using more gates because as soon as I see that one of these propagate bits is false, I just cancel out a whole bunch of my options. I just cancel out a whole bunch of terms. It basically shuts the whole thing down. Whereas if I do it this way, it's still kind of ripple-esque, right? It's still kind of like the carry ripple, where I have to wait for the carry bit to be computed before I can determine what I'm going to do next. So I think this way would still actually be a little faster than a carry ripple adder, but this way is the true carry lookahead, and it has to be the expanded version, right? Part of this section, if you went through the side book, which I hope you did, part of this section was talking about trade-offs. We're making a trade-off here. I'm using a lot more gates. I'm taking up a lot more space. What do I get in return for that space? I get speed. I get faster additions, right? That's what I get in return. So yes, I understand your point completely. But this is really important, an important part of the carry lookahead adder. To prove it, let's prove it. This one I'm going to turn you loose on for a few minutes, right? Here, this is a carry ripple. So this is the old way of doing things. We want to assume that each gate takes 2 nanoseconds of delay, right? So the question then becomes, what's the max delay for one of these guys? We actually already did this. We have the answer written down from before. You don't have to read it. We already computed the max delay for this guy. What's the max delay for this guy? It's got a whole bunch of gates, right? It's got a whole bunch of gates. Yeah, very, very short critical path, exactly. So take a few minutes, see if you can compute the maximum delay for this carry ripple and the maximum delay for this guy. You'll have to finish writing out these equations, probably, in order to answer this question fully. And if it makes you feel better to draw out the circuit, then by all means, draw out the circuit. It's going to get kind of large, I'll warn you. It's going to take a lot of gates. So yeah, take a few minutes, see if you can figure out the answer to this question. We'll talk about the answer in just a little bit.
Yeah.
Because the other one, so you have the C zero. Yeah, I was the one that you have C one and the trains into two, and then you have C two. Sorry, C zero locates into one, C one locates into two, C two, C three,
Wait, how do you get to
oh no, it is her. It's talking about a carry back to the first three and then this one. Because the sum of the four carry. Yeah. So the best part, what is the worst form of this book?
I was like,
That final term for C. See how the term where I can possibly right? Like each time we propagate down, yeah. CN. This could be CN will propagate. Oh, I see. It's an inverted and oh, because P1 is on top. Oh, I mean, I guess. Are we assuming multiple input angles? Yeah, you can assume multiple input angles. Okay, so you can do your 5 input gigantic thing. Yeah. So it's just the 2 inputs.
well, I mean, well, yeah. Well, you've got at least 3 gates here and stuff.
Oh yeah. Yeah, that's true. So it's not the
And the reason it lasts for the character You've also got 3 gates here. Yeah, E0 is computed. Yeah, right. So I will go
yeah. Because P is based on P is basically yeah. Yeah. Oh, no, actually, it goes to all figure six. That's what we do. Let's get to this is if we do that, it was absolutely we were talking about because of one hit, and the one person that actually like doesn't like some people You get like whatever government was, whatever government teacher, or person who did
No, first one.
literally focused on the value. First semester.
Okay, who's got an answer for me? What's the worst case for this carry ripple? We've already computed that. What's the worst case? How many gates do we have to go through, right? So it's all based on these carry bits. So carry bit has to go through, let's see, 2 gates for each of these, right, to generate the next carry bit. So it's going to be 4, 6, 8, or 4, 8, 12. And then for the last one, we have to take into account 3 gates because the sum path is actually longer than the carry out path. So that's 6, that would be 18, am I right? 18 nanoseconds for worst case with the carry ripple, right? What about this guy? How many gates do I absolutely have to go through? Or, I mean, what's the most amount of gates that I'm going to have to travel through in order to compute my answer? This one's a little bit trickier to figure out. What's the path? How does it work? Somebody explain to me. What do we got? Hopefully less. Yeah.
Well, so either in the sum or your carry path is sum is pretty easy to see.
Yeah, so sum is the same. This sum part is all the same, even for our carry lookahead adder. So that's exactly the same. We've got at least 3 gates here. At least 3 gates here. But these depend on the carry in, right? So they still depend on the carry in bits. I should make sure to emphasize the fact that these still do depend on the carry in bits coming in, so we can't count sum officially until we get that carry in value. So the question really comes down to how fast can we compute these carry values, right? How fast can we compute those guys? So what's the worst case scenario? The worst case scenario means we're going to compute G and P pretty fast. In fact, consider that G and P are going to be computed at the same time for each one of these, right? At the same time for each one of those. And we compute it simultaneously. How long does it take to compute G and P? 1 gate, so 2 nanoseconds. So we got 2 nanoseconds right there. 2 nanoseconds right there to compute G and P, right? So then we have to talk about how long it's going to take to compute carry bits once we've got G and P for each of these values. So I've got G and P here. How long does it take me to then compute whether or not I have a carry out bit coming out of here? Well, it could go as fast as 1 if G is high. If it's not, then it's going to take 2 more gates. So that's going to be an additional 4 nanoseconds, right? So we're up to 6 nanoseconds so far. And then this guy can get passed, except for, do we care about that for this one? No, we don't. We don't care about that one for this one. So let's consider how long would it take for this one to be computed then. Remember, G and P are going to pop out at exactly the same time, right? They're going to pop out at the same time here as they do here. So we're actually going to know this value at the same time. We're going to know whether this has a carry in, carry out bit at the exact same time as we know whether this has a carry out bit. Do you see that? We're going to know that at the exact same time. In fact, we're going to know this carry out bit and this carry out bit. All, not immediately, but at the exact same time, no more than 6 nanoseconds after we start adding everything up. Okay, do you see that? So then the question becomes, how long does it take for, I guess, this carry out bit to propagate through the sum side of things? It takes 6 nanoseconds, right? Because there's 3 gates there, so we end up with a total of 12. 12 nanoseconds, right? It's our worst case possible scenario. So that's 33% faster. Right, so the more, so the more bits we use, right, the more efficient this is relative to the carry ripple. That's true. Think about from the carry ripples, oops. From the perspective of this, if we keep adding on more bits, this is just going to take longer and longer and longer. If we keep adding more bits on here, does it get any longer? It doesn't get any longer. It just takes up more space. So if I stretch this out to, you said 64 bits, still 12 nanoseconds, but God, how many gates would that be? I don't know. A lot of gates. So in practice, what's actually done is we'll use banks. We use smaller banks, 4 or 8 bits, and chain them together. And that way we get the time savings without the massive space requirements that's necessary. In fact, consider that at the same time I generate these carryout bits, well, that's not the right diagram. At the same time I generate these carryout bits, I've also generated this carryout bit, which can be fed into another adder right next door, and we can begin the whole process over again, right? So that's where it really adds up. We can get the same savings over much larger binary values. So these are way faster, but again, more space. It's a trade-off. What about best case? What's the best case for a carry ripple adder? What's the fastest possible that we can get through a carry ripple adder? Is it any different? Is there any way I can get through there any faster? Well, I was talking about the carry ripple adder. I mean, we can talk about carry Lookahead too. If all the G's are high over here, then we don't have to go through as many gates. We get to shave off one gate basically. So it's negligible, a couple nanoseconds. Over here, I don't think there's anything we can do differently. I think that's it. Right? So it's kind of a trick question. The best case for the carry ripple is the same as the worst case. It's just the delay. It's just how long it takes. What it is. And really, for the carry Lookahead, it's pretty much the same thing. Could we possibly save some time in certain cases? Yeah, but I'm not going to count on it. The general case is going through the whole longest path. Any questions? Any questions about the adders? Any questions? Let's shift over to multipliers then. So here's a multiplier. Here's how we did multiplication. So how does this work? I've got 2 4-bit values. I want to multiply them together. So what's the deal here? Why do I see a bunch of AND gates? How do AND gates relate to multiplication? Yeah. It's kind of the same thing, right? So what are my values that I'm multiplying? I've got zeros and ones, right? So 1 times 1 is 1. 1 times 0 is 0. 0 times 1 is 0. 0 times 0 is 0. Oh, hey, look. That's a truth table for an AND gate. AND gates perform single-bit multiplication. So that's great. That's awesome. That's wonderful for us, right? So we see that for our 4 bits, I just start ANDing the bits together. So I AND everything with bit 0. Then I AND everything with bit 1. I AND everything with bit 2. I AND everything with bit 3. But just like we do multiplication for decimal, right, we have to keep shifting everything over a place to keep it accurate. So here, we're not multiplying by 1, we're actually multiplying by 2. Here, we're multiplying by 4, right? We're multiplying by 8, etc. So we have to keep shifting things over, and what that means is our result is going to have more bits than our starting values. So I have two 4-bit values coming in. I've got, let's see, it says 7 bits here, but then it has 8 bits here. I'm not sure what the deal is with that. Where did that extra bit come from? What did that extra bit? Oh, right. So it's taking a overflow bit into account. Yep, that's exactly right. So I have 2 4-bit values that are multiplying. I get 8 bits out. 8 bits back out. Right. So it's going to be a wider number. It has to be because I'm shifting everything over to keep track of that multiplication. So here's the question. We have these adders here, 5 bits, 6 bits, 7 bits. Here's the question. What's the delay going to be for this thing if I use carry ripple versus carry Lookahead adders? Take a couple minutes. This one shouldn't take too long, although do pay attention to the fact that these are different size adders. Pay attention to that fact, because that's going to matter.
There's that
Okay. Let's see if we can reason about this problem a little bit. For starters, these are constant, right? These end gates are constant. How much time am I losing because of all this mess? 2 nanoseconds because it all happens at the same time. All parallel. So all of these end gates are set in 2 nanoseconds. It's just one gate delay, right? So that's easy. That's going to be constant. I don't even need to write it down. We set 2 nanoseconds right off the bat. So for the carry ripple adder, there's actually a function you can use to determine how much delay there's going to be, right? And really, we've been using 2 nanoseconds for gate delay, but we can generalize it. We can just say how many gates are there, and that'll then convert to any gate delay we want based on the quality of the gates that we use. So if I want to know how many gates are in the critical path of a carry ripple adder, what's the formula that we use? Depending on what? The number of bits, right? So for each of these, how many gates do I have? I think it's just 2 plus 3 for the last one. So if I have 4 bits, it's 4 minus 1 times 2 gates, and then 3 plus 3, right? Add 3 on the end. So for 5 bits, that would be 4 times 2, which is 8 gates, plus 3 for the last one. So that's 11 gates total, and you can do the math and figure out the total gate delay based off of that. So we've got, if we look at each of these in order, we've got 5 bits, 6 bits, and 7 bits. Basically, we're adding, what, 4 nanoseconds for each additional bit for a carry ripple, 4 nanoseconds more. So we've got 22, 26, and 30, right? So that's 56, 78 nanoseconds plus the 2, and we're already up to 80 nanoseconds for carry ripple adders. That matches what you guys have. So, are there any problems with that number? Anything else that we should consider? Are these some bits all coming out at the same time? They're not. Actually, these are going to come out faster than these. Does that change anything? Does that change anything? No? Why not? So if we're talking about worst case delay, right, this is going to take the full 22 nanoseconds to finish up, and we're not going to be able to resolve this next one until this one's over. So we have to wait for that one to finish and then that one. Wait for this one to finish to do that one. In a more realistic scenario, is it going to take 80 nanoseconds? No, it'll probably take less. This is the worst case, right? So it'll probably take less. But we need to plan for the worst case. We don't want to cover most cases. We want to cover all cases. If we ever do run into a case where the maximum delay is reached, we don't want to break much. So we need to plan for the worst case. How long is it going to take if I use carry lookahead instead? How long does, what's the formula relative to number of bits for a carry ripple? It's just, it doesn't matter, right? They're all the same. The number of bits doesn't matter. It's just 12 nanoseconds a pop. Boom, done. So 36 nanoseconds plus the 2 end up with 38 for the carry ripple. So you can see how it really adds up, right? Sorry, guys. Couldn't resist. Couldn't resist. Yeah. All right. Let's take a look at a little bit of a different problem. Here's a little bit of a different problem for us. It may not seem like it's related to what we're talking about, but it is, I promise. So I have a 4-bit binary value. A 4-bit signed binary value. So 2's complement, right? 2's complement binary value. And I want to make this an 8-bit binary value that has the equivalent value. So if I give you -4 using 4 bits, I want to make -4 8 bits instead. Okay? Your first task is how do you need to alter the number to make that happen? So try a few of them out and see what it looks like, right? How do we change the number from 4 bits to 8 bits? What's -4 in 4 bits? What's -4 in 8 bits? See if you can see what the pattern is, and then see if you can design a circuit that will make that conversion for us. Don't forget about positive values too. It has to be able to handle both positive and negative. Yeah, I can kind of, yeah, I kind of. No, it's not like that. 8 hours later. It's big. Did you guys like it? We have, one is oh, it's the way that now these but we are cheating that we know these assembly instructions. Yeah. How does assembly matter? We're not talking about CPU necessarily. Because there is the assembly instruction for how you do extending. For whatever number, it's move S and then type to type BL will be L is long. Yeah. Yeah. And the S extends. Oh, oh, that's what I'm asking you to do. Yeah. I mean, that really is all right, let's talk about this one. Let's start with the easy. Let's start with the easy one. Here's 4, positive 4, using 4 bits. How do I make positive 4 using 8 bits? I just start tacking zeros on the front, right? Boom, done. Easy, easy. All right, let's try negative 4. How do I get from positive 4 to negative 4? I have to do the 2's complement, so I flip everything and I add 1 to it, right? So flipping everything gets me 1, 0, 1, 1, and then I add 1 to it, that gets me 1, 1, 0, 0, right? So here's -4 using 4 bits. Well, let's see what this one would look like. It would be 1, 1, 1, 1, 1, 0, and then I add 1, and what do I get? I get 1, 1, 1, 1, 0, 0. Right? So positive 4 and 4 bits to positive 4 and 8 bits, negative 4 and 4 bits to negative 4 and 8 bits. There's a very simple pattern going on here, right? What do I do? I want to make it longer. What do? I copy the sign bit however many times I want. I just take the sign bit, I copy it out until I get the size that I want. That's it. That's it. So the circuit should be a piece of cake. In fact, it's not really even a circuit. It's more like, 4 bits coming in to the box, and then these 3 bits just go straight down, and then this one just gets copied, right? 4 more times. Done. Okay, it's not even really a circuit necessarily, right? So sign extension is what this is called. Sign extension. We take a binary value, we take a larger number of bits, we extend the sign. Let's take a look at another problem now that we've figured that one out. So here's our multiplier. Does this work with signed binary values? I'll give you a hint. The answer is no. It does not. Can we make it work with signed binary values? That's the question that I have for you. Take a few minutes. See if you can figure out how do you make this work with signed binary values. So same number of bits coming in, but now it's a 4-bit signed binary. That means this first bit is a signed bit. How does that change things? Let me give you a hint if you want some help. Try and do a multiplication out on paper like you would and see what the sign bit should be. Right? See how that affects the multiplication that takes place. Take a few minutes. We'll talk about the answer in just a little bit. You don't have to draw the circuit, but you should be able to tell me what changes need to be made, right? To the circuit. got some suggestions for me? Who's got some suggestions for me? There are many, well, not many. There are at least multiple ways that I know to solve this problem. Yeah.
Well, if you have one or two negative numbers, you're just making both positive, do the multiplication as normal, and then if you have one negative number going in, you make your output number negative, and two negative numbers, you keep your output positive.
So we're basically just applying the rules of multiplication, right? So if they're both positive, we got no problem. We handle that just fine. If they're both negative, then what was it you said?
Make both the numbers
Negate them and then
Yeah.
multiply. So check the sign bit, negate things that necessary, and then continue. And then if one is negative, then you just multiply as normal and
then negate the output.
flip this or negate the output. Okay. I don't see any reason why that wouldn't work. We would need several components to make that happen, right? So we would need at least a few conversion operations to make that happen. So that's actually an additional adder for each negation that we potentially need, which is
I would have two adders.
3, right? One for each operand as well as the product, right?
Yeah, but only two.
That's correct, because the 2 at the beginning would both happen at the same time. Yep, that's correct. Yeah, I think that would work. I don't see any reason why it wouldn't work. We have to add some additional components. I mean, I don't think there's any way to do this without adding some kind of additional components. The only thing that I would be a little nervous about is the case when one is negative and the other one's positive. That's the only one that I would be a little wary of. But I think it works. I'm trying to think of what that would look like. What if we do, let's try an example. 2 times, 2 times negative 2 should get us negative 4, right? So negative 2 is this. Yeah. So what do we get? We get all zeros, then we get 0, 1, 0, 0, then we get 0, 0, 0, 1, 0, 0. So this is what we get, right? And then when we add it all up, we get 0, 0, 1, 1, 1, 0, 0. So I think here's the problem. This should be negative 4, and it's close, right? I see the 1, 1, 0, 0 at the end, but I've got 2 zeros up here at front. So just negating this isn't going to work. Because this is not positive 4. So if I negate it, I'm not going to get the right answer out. I think your operation would work for if they're both positive, if they're both negative. I think that would be fine. But if just one of them is negative, we'll just negate the one that's coming in. So you're saying negate the one that's coming in, not negate the result. I misunderstood. And negate the result. Oh yeah, so make them both positive and then just negate the result. I see. I misunderstood. Yeah.
Yeah.
That would work. Yeah.
It's just very simple.
That would work. That would work. Yep. Absolutely. Sure. Is there another way? The answer is yes, there is another way. Did anybody discover another way? Anybody discover something different? I mean, I did this example on the board, so maybe we can take a look at this and see if there's something that could help us out here. You see that it looks pretty close, right? It looks like I can see the negative 4, and then it just kind of falls apart here towards the end. Is there something we can do about that? Yeah. Just the last bit meaning the sign bit, right?
Well, in the answer.
Oh, so like
that one doesn't match our pattern, so I didn't.
Oh, it didn't match your pattern. Okay. I'm sorry? We wanted to get negative 4.
So if you avoid the first
Well, yeah, but the result of multiplication is going to be what? So I mean, I should expect 8 bits here, right? That's kind of the idea. So I can't just start chopping stuff off. That's not going to be productive to us. It's not going to be productive. Any other ideas? Anybody else come up with a solution? error exclusion is great. It does involve additional components. Is there a way that we can maybe use less components? That might be more beneficial, perhaps. Or did any of you think that maybe I talked about sign extension for a reason? Maybe I just brought that up to kind of help us think about this problem instead of just making up a random problem for you to work on. Sign extension can help us here. Anybody see how? Sign extension can help. No? Anybody see how? We sign extend the results, so the results already indicating to me that it's positive. So that's unfortunately not quite going to work out. Or maybe another way of thinking about this is actually here I'm taking this sign bit. That indicates that this is negative. And I'm doing this. All of our original multiples, so like these values, right? So I think that might help. It might not be obvious that it's helping now since we're talking about positive values, but think about if we were talking about negative values, then that might make sense. Also consider the case that I'm taking this sign bit, which is essentially a negative value, and I'm multiplying it by this positive value, right? So what should the result be? Negative. So what if I subtract this last value since it's in fact the sign bit that's there, right? I'm essentially negating this last value. What if I subtract this guy, and then what do I get? What do I get out of this? It might be a little tricky to figure this one out, but we've got this plus the inverse of this, basically. So if we invert this guy, we get 1, 1, 1, 0, 0, 0, 0. You see that the negation of this is 1, 1, 1, 0, 0, 0, 0. Do you agree with me on that one? Do you agree that this, the 2's complement of this is this? Yes? So then if I add these together, what do I get? 1, 1, 1, 1, 1, 0, 0. That's negative 4 right there. That's negative 4. So sign extending these is good, and then subtracting the last value instead of adding it is also good. Consider what's the case if this is 0. Well, I get all zeros here, so subtracting it's not going to do anything. So that's not going to matter. Only when I multiply by this negative sign bit do I actually see a true subtraction here. Subtracting 0 is easy. Let's try another example just to prove that it works. Let's try, we can try a few examples if it'll convince you that it works. So let's try maybe 2 negative numbers this time. Let's see what that does for us. So let's do negative 2 and negative 2 maybe, or negative 2 and negative 3. So negative 2 is, I just had it up on the board, 1, 1, 1, 0. No, that's not right. Is it? Yeah. No, that's right. And then negative 3, I don't know that I can do that one in my head. It would be 1, 1, 0, 1, negative 3, right? 1, 1, 0, 1. Okay. So let's multiply. So we get 0, 0, 1, 1, 1. But I'm saying sign extend this out to be the same length as your result. That's what I'm saying. So if I expect my result to be, what, 7 bits? I'm going to sign extend this out. 8 bits. That's fine. Okay, then I've got a whole bunch of zeros, so that's easy. Then I've got 0, 0, 0, 1, 1, 1, 1, 1. Is that too many? No, that's the right number. 8. And then finally I've got 0, 0, 0, 0, 1. I did something wrong, didn't I? No, I didn't. I think I'm okay. Have the right number of zeros. With the sign extension, it gets a little tricky. That's padding. That's 2 padded zeros plus that 0, and then 3 padded zeros plus that 0. Okay, I think we're good. So what am I suggesting that we do? I'm suggesting that we add all of these together, and then we subtract this result. So let's do the addition first, because that's usually the easy part, right? So if I add these together, I get 0, 1, 1. Then I have 0 carry. So that's going to be 1 carry, 1 carry, 1. Right? Did I do that right? That's just the addition of these guys, basically. posting this. Did I do that right? Anybody disagree? I want to make sure we're on the same page. 0, 1, 1. That's easy. 0, carry the 1. 1, carry the 1, carry the 1, carry the 1, carry the 1. Right? And then subtract this guy. So we have to take 2's complement of this and then add. So that's going to be 0, 0, 0, 1, 1, 1, 1, 1. Flip everything. No, that's not right, is it? That's not right. 3 zeros, a 1, and then 4 zeros. Thank you. We flip all these, we add 1, which flips. Yep, got it. And now we add again, 0, 1, 1, 0, 0, carry. That's going to be 0, carry, 0, carry, 0. So I end up with 4 and 2, which is 6. Negative 3 times negative 2 gets me a positive 6. It works. It works. I know it's a little complicated, a little bit complicated. We're not used to doing arithmetic like this, right? But so what are the changes I made? I sign extended my partial sums, and I subtract the last value instead of adding the last value. What does that mean in terms of my circuit? What does that mean in terms of my circuit? What do I have to do? Make things different. What does that mean? Sign extenders, that's easy. That's just wires, right? So sign extenders are easy. These have to be wider now. What does that do to my delay? Diddly if I'm using the carry Lookahead, right? Doesn't affect my delay at all. This last guy has to become a subtractor instead of an adder. That's not that bad. That's just a few inverters in front, right? That's basically it. Now it's a subtractor instead of an adder, and we're good. We're good. Is it going to take up more space? Yeah, because these are going to be wider. Maybe these are going to be 8 bits carry vectors, 5, 6 bits. So that's kind of the trade-off there. It's going to take up more space. But it works. It works. There's actually further optimizations that you can do. Even further optimizations that you can do that gets rid of the sign extensions. We don't have time to do that right now, so I'll leave that as an exercise for you to think about. And we'll call it a day. Have a good weekend. I'll see you guys on Tuesday.
Tuesday, but I think 2 weeks ago that I started exam too. What are your lectures
So next week I will be here on Monday from 1 until like 4 or 5 o'clock, and on Tuesday from 1 until like 4 or 5 o'clock. So 1 until 5 o'clock. So 1 to 4,
Okay.
roughly.
And you're in Bryan, right?
I'm in Bryan now, yeah.
Right, Chris.
Bryan 223.
Okay.
Yep.
Mr. Show?
Yeah.
I have a question about this time.
Uh-huh.
I traveling with planes recently, and I was wondering if it was possible to take the exam 1 day before. Would really help out, but I really haven't bought tickets, so if it's a definite.
I need to think about it. Why don't you shoot me an email? I know you need to buy tickets, so I'll try and decide sooner rather than later. But let me sleep on it tonight, and I'll get back to you tomorrow.
Okay, sounds good. Thank you.
Yeah.
Okay, so now for 40 have it as optional right now.
That's correct. Yep. Yep.